Thank you, Brian. What I'd like to report on today is a study that was conducted in early January of this year, but started in late October of last year. At that time, Dr. Leslie Hebb of Vanderbilt University had some issues with M-dwarf binary pairs, and particularly she was concerned with the discrepancies between the models of these binaries, radii, and their masses. The models did not appear to jive and were about 10% off from the actual values. She went to Dr. Bruce Gary of Hereford, Arizona, and said, I think I'm going to do some studies on this, and in fact I have some funding to do some spectropolarimetry of YY-GEM and see if we can understand what's going on there. What I'd like to report on today is the amateur side of that collaboration between Dr. Hebb and Bruce Gary and the amateur team he put together. This is an image of YY-GEM. It's in the yellow circles. Notice there's another bright object, which is Castor, 71 arc seconds away. Castor at 1.5 magnitude, YY-GEM at 9, gave us a difference of about 7.5 magnitudes. This image shows some of the diffraction and reflection effects of pixels from Castor. A similar problem resulted, this is another image from one of the other team members. YY-GEM is just down to the left of Castor, and you can see that in order to get any kind of signal at all, we had to do some exposures that were caused Castor to bloom all over the whole chip just about. Also, you notice the next brightest star in this image is just about on the diffraction spike from the secondary of the telescope that this image was taken from. So there was a lot of technical problems in trying to measure the brightness of YY-GEM in support of Dr. Hebb's work. What she was looking for is to try and understand why the models of this binary M-dwarf pair did not jive with the actual measurements. And she felt that it might be due to some magnetic fields causing some star spots, both polar star spots and regular star spots. And she got this funding to try and understand this, and she received funding to do a 10-day run on the Canada-France Hawaii telescope, the 3.6 meter telescope there, with the spectropolarimetry and try and understand what the magnetic fields and magnetic effects were on these pair of stars. Particularly, she was curious about what these star spots were doing, and she felt that she could get the data from that. Her run started in January 4th of this year and extended to January 13th. And prior to that, in last October, she approached Bruce Gary to see if he could put perhaps an amateur team together and provide some high-resolution light curves of this object. He approached a few of us to see if we could figure out what the light curve shape would be, what the changes in shape might be, particularly understand out of transit, the out of transit light curve and the shape of the out of transit light curves. And of course, these are M-dwarf stars. They're going to flare, and those flares would affect her measurements, and she wanted to do some correlation in that. The question really was, can amateurs do that? And that's what the October series of measurements were all about. Bruce collected up some amateur exoplanet observers from around the world and said, would you like to join this team, and do you have the time available to do this in January? A number of us said we were available, and so he gave us our targets and talked to us about what the problems were going to be with the star and what Dr. Hebb really wanted to do, and that was a wide wavelength coverage and a wide longitudinal coverage, and hopefully having light curves that all overlapped. She also indicated that she had no money, and she would be willing to pay the amateurs nothing to do this data, and of course, being amateurs, we all jumped on board. This is the team that ultimately was put together. It consists of 9 amateurs. You can see from the first column it had a very wide longitudinal coverage, all the way from Greece to Japan. You can see the instruments for the most part are relatively modest equipment. Strangely enough, they all had Santa Barbara instrument cameras, but of different types. You can see we arranged all the way from 6s to 10s. And more importantly, we all had a series of filters. And in October, when we were sort of rehearsing this January run, we took images of YYGM in all the filters we had, and then Bruce went through and selected the appropriate filters for our longitude to give us the right coverage. I might note the subscript S on some of these filters are the RGB filters supplied by a Santa Barbara Instrument Group. So there are photometric filters on there, there are RGB filters on there, and it gave us a fairly wide coverage. You can also see there were some G, R, and IZ prime filters in that group. Well, in order to do this work and to connect up the light curves, we needed to use one reference star. And the reference star that was selected is that one labeled number 1. And so we did an all-sky calibration of that star in all filters and got the information to use that as an appropriate reference star for this study. Typical light curve. This is a primary during session number 4, night number 4 of her run. It was taken in R, and it was produced by Srdac in Croatia. Very nice primary eclipse, and a very nice flare after the primary eclipse. In fact, that flare was measured by 7 or 6 of the observers. This is by Zambelli in Italy in blue, much higher than in red. And combining and looking at all of those light curves of that flare, the 6 that were recorded, you can see a very progression in amplitude from red to blue that occurred. Also note it's sort of a double-humped light curve, or double-humped flare, and that was available in all of them. That flare and the fact that it was recorded in 6 different wavelengths allowed us to to compute a spectral index of that flare. And this is a log-log plot, so it's a little bit hard to get your head wrapped around, but it's a fairly linear relationship in that type of plot. Flares occurred all the time. Here's a flare that occurred during a secondary transit. Again, instead you can see the double hump aspect to it, and very interesting. This is recorded by Zambelli in Italy. When we combine all the light curves together that were recorded for this run, we have a very clear secondary and primary transit. And I'm going to give you a second to look at that because you might say there's a mislabeling. Typically the primary transit is the deepest one and the secondary is the shallower one. In this case, we have labeled them correctly, we believe, and we find the secondary transit deeper than the primary. We arrived at the secondary primary designation from some data taken in 1971 in BVNR, and this data very conclusively put an ephemeris together with some fairly tight error constraints, and carrying that ephemeris forward for decades, we gave a pretty convincing argument that we had the labeling correct, and that argument is in the printed proceedings if you want to go through and see why we feel that we are correct in our current labeling. So what's making this difference? Well, we think it's star spots. But before we get to the star spot answer, let me show you the comparison between the secondary and primary eclipse depths from the work that was done in January of this year compared to the work that was done in 1971. The blue circles, the blue solid circles, are the secondary transit depths versus wavelength. The red solid circles are the primary transit depth from 2012 observations. Included in these are the open circles from the data from 1971. And in this case, you notice the primary depths are going right along with the secondary depths, and the secondary depths are going right along with the primary depths. So something has changed. We feel pretty certain we have a good argument for the labeling of primary secondary, and we also feel that we understand why this picture occurred. I might note that these two stars are about 6/10 solar masses. They have about a 19.5-hour period rotation. So we felt pretty confident we understood the ephemeris. What are these explanations for these change and what would be a secondary and what would be a primary designation? Well, we think the answer is star spots. And we think star spots existed on both stars. They're caused by magnetic field concentrations inhibiting the solar convection. We think there were changes in star spots between 1971 and in 2012. Do we have clear evidence of these star spots? And I think we do. Following are some out-of-transit light curves. You can see the variation between the two transits. This was taken in G prime, and as we go through the various wavelengths of this, we notice, keep your eye on the out-of-transit variation. The variation becomes smaller as we go down. Here it is in Z-band. It's almost gone, the variation. This is pretty clear evidence, we believe, for the star spot activity on these stars, and we think this is what's causing the variation in depth in the two different transits. The out-of-transit amplitude versus wavelength, again, is a nice linear plot, again, proving our position on this. Well, Dr. Hebb has not had a chance to completely categorize and analyze the data that she took, nor has she had a chance to interleave it with the data that we took. But during that time, she was able to pick up 34 average ion V-Stokes velocity profiles. She had a very high signal and noise on her measurements, so she feels pretty confident. She has some strong data. Star spots maps for both of the stars look very good. And she's found 2 spot complexes on both stars with no polar spots. The analysis is still underway, and she'll be publishing that, we hope, in the fall of this year. The amateur observations, which actually collaborated her work and gave her some key information, there were 9 observers. We observed in 8 bands. We obtained 127 light curves. 93 of these were done during the 10-day run that she had on the CFHT. 44 complete transits were measured, and prior to her 10-day run, we had 56 non-overlapping hours of observation, and during the 10-day run, we had 180 hours of non-overlapping observation. Notice also that there were considerably more flares in January than there were in October. We only measured amongst the group 1 flare in October and 20 in January. And those flares really provided a lot of excitement to the observing team. We would get up in the morning and analyze data, and the emails would flow back and forth. Did you get the flare? Did you see it? No, I didn't see it. And, oh yeah, it was wild. So it was there was a lot of excitement doing this. So it wasn't just an ordinary, eclipsing binary run. It was looking for these flares that occurred. Some of the amateur findings during this 10-day run, the flare activity was considerably elevated, and this is going to prove very interesting when combined with her spectropolarimetry data. And so we're kind of all looking forward to find out exactly how that's going to turn out, because she caught all of these flares. Accurate transit shapes and depths were done in a wide variety of wavelengths. And the star spots were definitely there as evidenced by the out-of-transit activity that occurred. Some final thoughts. This is another example of pro-am collaboration where the work that she needed to do exactly fit in with what the data the amateurs could provide. And so it was a funny project, and any of you that have an opportunity to do something like this, I highly encourage it. It was a lot of fun to do. That's it. Any questions? Thank you.